Hello and welcome. We would like to wish everyone a good morning, a good afternoon, or a good evening, depending on where you are in the world. My name is Jamie, and I'm one of the co-founders of Safeopedia. Before we get started, I'd just like to run through a few housekeeping items. Everyone on the webinar will be on mute for the duration, but we really want to hear from you. So we'll keep it interactive and ask that you type all of your questions into the GoToWebinar console as we go. And we'll do our best to answer as many of them as possible at the end of the presentation, keeping this a very interactive safety talk. Also, today's webinar is being recorded, and we will be sending out a link to the recording and the slides to all participants after the show. Typically, one of the first questions that gets asked is, how do I get in touch with these presenters after the webinar? So what we'll do is we'll put up a slide at the end that has Doug's contact information. That way, if we don't get to your question or the webinar ends and you have a question after the fact, you can follow up with him directly. Today, we're proud to present Fall Safety, Physics, Statistics, and Fatalities. At Safeopedia, our goal is to support EH&S professionals, operational folks, and really all safety-minded individuals through high-quality educational content and resources. We'd really like to thank those dedicated professionals for the great work they do on a daily basis. It is now my pleasure to introduce to you today's presenters. Our host, Calvin Simpson, graduated with a diploma in Instrumentation Engineering Technology from NAIT and has had an in-depth involvement in all stages of the safety instrumented system safety life cycle. Through this process, Calvin has found a passion for safety deeply rooted beside his passion for life and believes that no worker should leave work any different than how they enter through the gates in the morning. As host of the Safety Talk Show, Calvin has the opportunity to find the most purpose and passion-driven safety professionals in the industry today. Our expert, Doug Myette, is a mechanical engineer with experience in design, manufacturing, and project management. Since 2008, Doug has worked strictly in fall protection and is a qualified fall protection engineer. He has designed fall protection systems for and consulted with clients in various industries, including construction, municipal government, provincial government, transportation, Class 1 railway, oil and gas, and agriculture. Doug is a professional member of APEGA and ASSE. Calvin and Doug, take it away.
Awesome. Well, thanks for that fantastic introduction, Jamie. It's great to be here, and thank you for everyone for joining us today. We'll hop into it right away because we want to stick as much to the content as possible. But before we do that, just a little framing about what Safety Talks is. So Safety Talks is really an evolution in webinars driven from a couple of Safeopedia's core values. Users first being one, or our participants on the line, as well as educational as well. So we want to make sure that we're giving all educational content to you listeners today. You're not going to hear any pitches for products from Doug. We want to also make sure that we're listening to everyone in our community, and we found that webinars in the past have really had some pretty dry content to them, which educational can be. So we really want to focus on bringing entertaining presenters in like Doug, as well as sticking to the mindset of, hey, we want to solve your problems today. So we asked every person before signing up for this webinar today or for this safety talk to ask us a question. So we're going to do our best to cover that in a 40-minute question period right after Doug's 20 minutes educational topic. And if you think of any questions throughout, please feel free to type them in the chat box, and we'll answer as many as we can. As I mentioned in the follow-up, as well as Jamie, we'll be answering any questions that don't get answered during the show after. Everyone also has the opportunity to schedule a 15-minute phone call with Doug to help them out with any issues they have today. So with no further ado, that's Safety Talks, and we'll hop right into it with Doug Myette.
Hello, everyone. Welcome. I hope you can hear me well. Okay, we're going to get right into the presentation here. Thanks for the introduction, Jamie and Calvin. I'm excited to be here today to bring to you this presentation on the physics of falls and the fall statistics and fall fatalities, which is a topic that I don't think a lot of people are aware of. So that's why we decided to do this presentation. So we're going to start out with the physics of a fall, of a falling object, breaking it down from the physics standpoint of what actually happens the false statistics from various sources around the world, and then a summary of the of fall fatalities. And it's quite surprising what you're going to see in this summary. So let's look at the physics of a falling object. So we're going to go right back to Isaac Newton's laws of motion, and then we're going to review the equation for motion for position of an object, because we're interested in how far we're going to fall in a certain amount of time. So Sir Isaac Newton was around in the 18th century, and he developed the Newtonian physics and the equations of motion, which were first published in 1687.
It's a long time ago.
Over 300 years ago. So this is not a new thing. We've known about these equations for a long time. And if there's any engineers out there, you know these equations from science class. And this is basically applied physics. So, getting right into the equation. Equation for motion of a falling object, or the equation for position, is represented by x equals x naught plus v naught t plus 1/2 at squared, where x is the position of the object that we're interested in. X naught is the initial position of the object at time interval 0. V naught is the initial velocity of the object at time interval 0. And t is the time interval, and a is the acceleration of the object. So when we're talking about a falling object, and oops, here's our little object falling. There she goes. Oh, fell too fast. Anyway, so we have the acceleration due to gravity, a equals g, where g is in metric units 9.81 meters per second squared, or in feet units it's 32.2 feet per second squared. And although there are variations around the globe, they are so minute that they're irrelevant in this discussion. And unless you're dealing with microparticles, I don't think it's going to matter where you are on the Earth. 9.81 meters per second squared is pretty much constant. So we're going to simplify this equation by getting rid of some of these values. So if we assume that the initial position where we start from is our reference point, so x naught equals 0, and we assume our object is not moving before it falls, so v naught equals 0. These two terms can be taken out of the equation. They go to 0. So we're left with a simple equation. And then if we substitute h for x, because we're interested in the height of the fall, and in our little equation here, our little picture here, we're going to substitute a or g for a, we're left with this very simple equation. The height of the fall equals 1/2 gt squared.
So here's a question, Doug. It's fairly, the question always comes up, and we answered it before. Say I'm 220 pounds, someone's 120 pounds. I don't see mass anywhere in this equation. So where does that factor in, or does that factor in?
Mass, it doesn't matter. Everything on the Earth is attracted to the Earth at the same rate. The same gravity affects everything on the Earth. I don't know how much people know about Einsteinian physics, but Einstein looked at the curvature of space-time, and it gets quite complicated, but that's why we're sticking to Newtonian physics, because it's quite straightforward. But when we look at the curvature of space-time, even the moon is held to the Earth due to the Earth's gravity. So you can see that the gravitational field of the Earth is quite large. It extends out quite a distance from the planet. And because humans are relatively close to the planet, within, depending on your elevation of where you live, I think the highest city in the world is, or at least in North America, is Denver, Colorado, at a mile high, 5,000 feet. Mm-hmm. We're currently sitting at about 3,500 feet in Calgary. And so,
fall the same rate?
We're all falling at the same rate. Everything falls at the same rate within the relatively close proximity to the Earth that we are. If we were at the top of Mount Everest, which is uninhabitable by humans because the elevation is way too high, you may fall at a slightly different rate, but for the purpose of this discussion, it doesn't matter.
Perfect.
So now we're going to carry on and we're going to simplify this equation even further. So I'm going to work in imperial units, that's keeping it in feet, because it keeps the math really simple. And you're going to see how this is something that you can take away from this to talk to your colleagues, coworkers, even your workforce, and explain to them how fast something falls. And it's very simple. So we're going to use 32.2 feet per second squared. We're going to substitute it in the equation, and you can see that h equals 16.1 t squared. And we can simplify it even further by rounding down to 16. So we're left with this equation, h equals 16 t squared. Now I'm going to put up a little timetable here, a little table here with times. So one of the things that I like to explain to people is, what is your reaction time? Reaction time is something that when you're anticipating an event happening, and by the time you react to it, that is your measured reaction time. So sitting at a red traffic light and waiting for it to turn green. When it turns green, you go. Your reaction time from the time it turned green to the time you go is how long that took you to realize, oh, I can go now. So that's an example of reaction time. So the average reaction time of any human on the planet is around 1/4 of a second.
That's when we're paying attention.
And that's when you're paying attention. So let's put in 1/4 second. So 1/4 second squared is 1/16 times 16 is 1 foot. You will fall 1 foot in 1/4 of a second. Anything will fall 1 foot in 1/4 of a second.
Half our reaction time, a foot.
Yeah. Yeah. So now if we doubled that reaction time to 1/2 a second, which is, you know, basically, if you're working at height and you're focused on your job and you're focused on bolting a flange together, or adjusting a valve or taking some measurements, doing an inspection, for example. Say we doubled it to 1/2 a second. Now let's put 1/2 a second in the equation. In 1/2 a second, you're going to fall 4 feet. So by the time you realize that you're even falling, by the time you react to that, you've already moved 4 feet. So if you think that you're going to grab something and catch yourself, most people's arms aren't even 4 feet long.
Yeah.
Maybe Calvin's, because he's 6 foot.
6'4".
6'4". He's a big guy.
Don't want to take my chances though.
No, and then there's other things that come into that. The stopping distance, the forces required to stop the motion of your mass, which is where mass comes in. That's the whole other equation. So 1/2 a second, you're going to fall 4 feet. Now let's double that again to 1 second. And you can probably already do the math and figure out how far you're going to fall in 1 second. 16 feet. 16 feet is the average height of a rail car, a truck, a transport trailer truck. It's a little more than the height of 1 story of a building. Maybe the height of the roof of a 1-story industrial building, 16 feet, or a house.
Yeah.
You know, if you have a roofing business, or you're in the roofing business doing shingling or construction of residential houses, 16 feet is a pretty common height to work at. And, you know, that's a life-changing event in 1 second. It's also another interesting value because most fall arrest systems will arrest your fall within a distance of 16 feet if they are connected and used properly. Which also tells us that a fall arrest event, from free fall, deceleration, and arrest, takes less than a second. Very, very fast. So let's double that again to 2 seconds. How far do you fall in 2 seconds? 64 feet.
Yeah, it's a shocking number for sure. And one of the questions we had earlier is, I'm going to be up on a roof for a very short amount of time. Do I need to be tied off? Should I be wearing fall protection? And when we look at 2 seconds and 64 feet, 1 second alone, I mean, that's a life-changing event from 16 or 64 feet.
Yeah. And that's a very good point. These heights that are shown here, 16 feet or 4.9 meters, or 64 feet and 19.5 meters, I'd like you to take those numbers and just jot them down or remember those values, because when we get into the statistics of fall heights, you're gonna come back to those numbers and you're gonna see and relate that back to that 1 second or 2 second time interval, and you're gonna see how long it took someone to die. And unfortunately, that's the reality of it. So that is the end of the physics part of this presentation. It's just to bring the numbers to people's attention. So now we're going to get into some fall statistics from various sources. And we're going to review by the industry, the mechanism of the fall, how did, the most common ways that people fall, the heights, but what are the average heights or the fatal heights that falls can occur from, and the review of worker ages, who falls, which age group falls the most or has the most fatalities, and then the summary of the statistics at the end. Mm-hmm. So here we go, by industry. So the first source that I'm bringing to people's attention is the U.S. federal OSHA has published this staggering statistic. Out of the 4,300 fatal falls or fatal injuries in industry in 2014, there was 900 of them were, or 20% was in the construction industry. And it's kind of not surprising. It's a very difficult. There's a lot of things going on a construction site when buildings are being built or bridges are being built or anything. There's a lot of things happening there. So the leading cause of death in construction was falls, and you can see there it's about 40% of the injuries or fatalities in the construction industry were due to falls. So a very high percentage.
It's a worker a day when I look at it.
Yeah. Yeah, 359 out of 899 deaths. And then here's another interesting stat. Out of the top 10 most frequently cited violations of the U.S. federal OSHA in 2015, from October 2014 to September 2015, so very recently, fall protection in construction was the #1 violation. And looking at the statistics of the fatalities in construction, it's not surprising that the #1 violation of the code is fall protection. Mm-hmm. So that's the United States, and I'm not going to pick on the U.S. anymore. So now we're going to look at some information from Australia, from Safe Work Australia. In 2014, out of 188 worker fatalities, which is much lower than the U.S., 47%, so the higher percentage was in agriculture, forestry, fishing, transport, postal, or warehousing. That's how it was grouped. Mm. And 15% were in construction. So 15% in Australia, 20% in the U.S. Those numbers aren't too far off. They're lower than in total, but they're comparable. So the leading cause of worker fatality in the workplace, first of all, was vehicle accidents, which isn't surprising because we all know that car accidents are the leading cause of fatality anywhere. And the second leading cause was due to falls. So there it is again. 11% of all fatalities in the workplace was due to falls. So 11% in Australia. And I don't know if that's because they're a safer country or they have better regulations or they've got better trained workers or it's just a population difference. But
yeah, we look at the numbers. I mean, #1 in U.S. or OSHA, #2 in Safe Work Australia. I mean, they're both up there. So
it's very like here we have two opposite ends of the world basically. Mm-hmm. So now let's look at mechanisms of falls. How do people fall? So from the National Center for Biology Information, which is a medical resource for sharing medical reports on various things, they had some reports on fall injuries. So in the United States in 2011, so 5 years ago, this is from, falls remain the leading cause of unintentional injury nationwide. Among workers, approximately 20% were due to falling from a ladder or involved a ladder. So the ladder is being targeted now. That ladder climber guy. And here's some more numbers, but a lot of information. Among construction workers, estimated 81% of the fall injuries involve a ladder. So now we know where the 40% of the fatalities in construction was from. Most of that was from falling from a ladder. So of the ladder falls resulted in 9% of those falls resulted in fatalities. And then an estimated 15,400 non-fatal injuries reported by workers resulted in a 1 or more days away from work. That's a lost time injury. Lost time costs money.
Yeah.
If you train your workers properly so they don't fall, you will save money from lost time injuries.
Yeah.
It can be correlated back to cost. Not only the cost of the fatality is saved, but the cost of the lost time is saved. And then an estimated 34,000 non-fatal injuries were treated in emergency room departments.
Yeah, I think it's always important to remember here, too, that obviously cost is incredibly important to any company, but when we think about I'm a worker out of site and I fall off a ladder and maybe it isn't maybe it is non-fatal, I still have something that's severely altered how I arrive to work, and I'm going home differently to my family, my kids, my wife.
Yep. You're not leaving work the same way you entered the gates in the morning. Exactly. So let's move on. So another bit of information I found there was from work-related falls from ladders from a study of emergency rooms. And ladder falls comprise 16% of all U.S. workplace-related fatalities. I don't know what year this was collected or published or studied, but the information is still applicable here because it falls in place with what we see earlier of the 81% due to falls from ladders. They're saying 16% of all U.S. work-related fall injuries are due to ladders. And then particularly hazardous among older workers. So here now age factor is coming into it, it's being introduced. Of the 306 workers experienced fall from an injury, the average height was 7.5 feet.
Yeah, so I mean, we go back to our first few statistics there, and when we look at 7.5 feet, I mean...
And let's put that 7.5 feet into that time interval we also studied earlier. In 1 second, you're going to fall 16 feet. In a half a second, you're going to fall 4 feet. So somewhere between a half a second and 1 second is the 7.5 foot mark. Probably closer to a half a second, but still, doesn't take long. You're done. So fall from a step ladder, extension ladder, various things. Primarily construction. Again, there's that construction industry again.
Yeah.
And then workers were most frequently standing or sitting on the ladder. So that's things you're not supposed to do. Stand on the top of the ladder or sitting on the top of the ladder. And installing, hanging, performing repair, whatever. But ladder movement was the mechanism of 40% of those falls. So the ladder moved somehow. So it wasn't secured properly. Again, it's probably due to cutting corners, complacency, not following procedures. I don't want to blame any one particular reason, but there's obviously something going on here.
Yeah, it's probably a good time to interject one of the questions that we had before. So how do you get people's attention to the risk and potential severity outside of signage, polite reminders, seize hand rails, and put away cell phones?
Education. Educate your workers. Have your workers understand what's going to happen. A lot of people that I've trained over the years think that, well, I'll just catch myself. And I I politely tell them that they're not a cat. They will not right themselves. They don't have the physiology to sustain a large fall. We're human beings. Human beings don't have cat-like reflexes.
Yeah, I mean, even just being aware of that table, I'm sure not too many people understand, hey, half a second, my reaction time, I fall this far, 16 feet.
You constantly accelerate downward. That's why it's called an acceleration due to gravity. So the longer you fall, the faster you're going to move. So the distance you travel increases as the time increases, and it increases because it's a squared term. So that it goes 4 feet, 16 feet, 64 feet. It's 4 times faster, more each time. Each time interval, as we double our time interval, we quadrupled the distance we fell.
Yeah, and a correction on that time, it's 4 feet in our reaction time, so 4 feet and half a second, correct?
Yes.
Yeah. Another interesting point that kind of addresses this question here is, I heard the other day, one of the facilities, they were putting up signs that an incident had occurred here. Say it was working from heights, and there's some sort of racking they would stick up if someone's fallen off from there and injured themselves. And it's a constant reminder of, hey, when you're using that, if someone's hurt themselves from here, and they saw really good improvements in not only their culture, but their statistics just from putting a sign that someone had been injured here. So it's something to keep in mind too.
Yeah, that's a really good technique.
Because it's constantly reminding, and it makes it real. I find a lot of the time safety, as professionals, we have a tough time making it real because some of these things don't happen that often, or we're not there all the time. So having that reminder of a sign of, hey, one of your coworkers is injured themselves here, can be a pretty powerful tool.
Yeah, definitely. We don't like to target the injured worker or single them out, but sometimes that is the message that needs to be put in people's faces as a reminder. So now let's move on to the height statistics. So the National Center for Biology Information again, biotechnical information. So falls from height, injuries, and mortality this is out of the UK. A study that was done from 2008 to 2009, so going back 7 or 8 years, but still valid today. So the injured or deceased patients following a fall from height, age 16 to 16 and over, out of the 117 patients, the mean age was 37 years, so a little bit older group, and the mean height. And out of that group, 29% were fatal. And the mean height here of the height fallen, so this isn't fatalities, this is just overall height of everyone, was 32.5 feet. So that's probably about a second and a quarter. Don't know, don't have my calculator, and I can't do the math in my fast anymore. It's very fast. Didn't take long for those people to fall to the ground.
Yeah.
And then in the group that died, in the 29%, the mean height was 55 feet, which is, so we're getting close to that 2-second mark. So in 2 seconds, their life ended, less than 2 seconds. And then this is a great bit of information I found on the Great Outdoors Stack Exchange website, and this is interesting. How far would you have to fall to be fatal? And remembering that it's not the fall that gets you, it's the sudden stop at the end. I thought that was a great quote to add here. So this is some interesting data from NASA, research they did on ejection systems and acceleration on the human body. So basically the summary found this. Up to 12 meters per second impact velocity, you are almost certain to survive. And that's corresponding to a height of about 23 feet. Which would take you, this is a second and a quarter.
Yeah.
Not very a second, just over a second.
At a second, we're at 16 feet.
And then you notice they say, and survive is likely a life-changing event, like you now have a limp or worse, you're quadriplegic or paraplegic, confined to a wheelchair for the rest of your life.
Your life has changed.
So Calvin and I were talking about these values earlier, and 12 meters per second or 39 feet per second don't really mean a lot to the average person. Yeah. So I said, well, why don't I put it in kilometers per hour? So 43 kilometers per hour, and in miles per hour, that's about 21 or 22 miles per hour. So imagine hitting the ground at 43 kilometers per hour, or being hit by a truck at 43 kilometers per hour. You're likely to survive, but you're probably going to be have a life-changing event. You'll be in a wheelchair. Now let's look at the next grouping that they found. From 12 meters per second to 17 meters per second, you may or may not survive. So now we're at the risky area here, and that's corresponding to a height of 23 to 39 feet, or 7 to 12 meters. So it's iffy at that point.
Yeah.
And then over 17 meters per second, you're almost certain not to survive. So that's a fall of 12 meters or 39 feet or higher, which, if we look at the statistic above, the mean average height of the group that died was 55 feet or 16.7 meters.
Yeah, I really like the 43 kilometers per hour, and I'd encourage everyone to take that away. It makes them much more real at that point in time when workers understand how fast they're traveling at a certain height.
Let's make it even more real. Let's change that 17 meters per second to kilometers per hour also.
Yeah.
How's that for value? So if you're hit by a truck between 43 and 61 kilometers per hour, you may or may not survive. If you're hit by a truck traveling faster than 61 kilometers per hour, most likely not going to survive. And that's, in 61 kilometers per hour is, I think, 53 miles per hour.
It's a physics portion, so important.
Yeah, if you have a conversion calculator, you can convert those numbers. But interesting values. When we put it into values like that, it really makes sense. So let's look at the next group.
So you were also telling me, I think this is an interesting story to share, a documented case of someone surviving from a fall.
Oh, yeah. There have been cases, rare, that people have fallen out of aircraft. There was a case of a woman fell from an aircraft 33,000 feet and survived.
Yeah.
How she did, it's a miracle. And the term survive is she's alive. She's not. She didn't get up and walk away by any stretch of the imagination.
Yeah.
But there have been cases where parachute, recreational parachuting, they've jumped and their chute has failed and they've survived the fall. So these things do happen. But
I think that's an interesting story to take away to, say, a safety stand down, is you can bring that story in that's interesting, but then also bring in the more realistic side here of the 43 kilometers per hour and the average statistics too. Makes the safety moment a little more interesting, as well as it brings us kind of back down to reality, right?
Yeah.
Hey, this is the situation.
Yeah, and there's quite a difference between accidental fall due to falling out of an aircraft, or recreational falling, as in skydiving or mountain climbing or one of those activities. But what we're talking about in safety talks is workplace fatalities, working. Like as Calvin said, going to work in the morning and leaving the same way that you entered the gates in the morning, healthy and safe and in good physical condition, uninjured. So workplace fatalities. Okay, so we're going to get on to worker by age groups. So fatal falls among construction workers from 1992 to 2008, over a 16-year period this study was conducted. So a very long period of time. Older workers had higher fall rates than younger workers. Falls from roofs accounted for 1/3 of construction fatal falls, but falls from ladders caused a large proportion of older workers than younger workers. So here's the ladders coming into it again. And in construction. But older workers. Here's out of Australia, over an 11-year period from 2003 to 2014, the highest number of workplace fatalities was in the age group 45 to 54. So again, the older work group. I'm not young.
You're thinking about retirement, man.
We're thinking about retirement in those years, and I think a lot of that may be due to confidence and complacency. The older worker tends to be the supervisor or the foreman or the inspector, and because of their years of experience on the job, so now they've been promoted to a position where they're not doing the physical labor, but they're there to review the work that's done or inspect the work or make sure things are installed correctly or just verify that things are good to go before the work is buttoned up. So you get the older guy going in there, and he says, well, I don't need to use fall protection because I know what I'm doing. And then he ends up on this page as a statistic.
Yeah.
So now we'll just get to the summary.
Yeah, we'll hop to those questions right away. This will be the last slide, and we'll get into what matters most to you now.
Yeah. So the industry, leading industry was construction, and 40% chance of a fatality in the construction industry. Mechanism of falls was ladders, where you had an 81% chance of a fatality from a ladder. The height, here we have 2 to 4 meters. Believe it or not, a 2 to 4 meter fall is sufficient to cause a fatality. And when we combine all these factors together, you'll see where that 2 to 4 meters comes into play. But you got a 55% chance of falling from 2 to 4 meters. The age group is 45 to 54 years. Mm-hmm. So 70% of fatalities occur in this age group. And the cause of death, blunt head trauma. 47% chance of dying from blunt head trauma. So we can sum this up by saying you can have a 47% chance of dying from a blunt head trauma if you're 70% chance in that age group from falling from that height from a ladder in the construction industry.
Yeah, I think that's a good way to put it. Blunt head trauma. I mean, tripping head first.
Yeah.
The issues are, and when we look at 2 to 4 meters, I mean, falling from 6 feet and above, hitting your head, I think it's pretty clear at that point. But also another cool table to show potentially employees in stand down to bring in some extra information that perhaps I haven't seen before. So that was fantastic, Doug. Thank you.
Thank you.
I'm going to pass this presentation out after, but for any assistance with your fall safety program, feel free to contact Doug here. And with that, we'll hop into a few of the questions that we had coming in. So let's get into one of the questions that we had from before. So do you believe the application of more standards and codes are the only way, or only are the best tools to perform safety without failure, or some other parameters related to humans are necessary for safe operation? So standards and codes, is that the best tool to improve our performance in fall safety?
No, I don't think that that having more standards or codes is going to solve your fall protection issues. What's really going to help have a safe work environment is educating your workers, giving them adequate training in fall safety, providing your workers with good equipment, good systems, and well-written procedures, so that they understand how to use the equipment properly, what's going to happen when they fall, how to rescue the worker after they've fallen. All these things are much more important than having rules and regulations that the government has placed on us, or an organization like ANSI or CSA or the EN standards, CE directives, all these other things that are out there in the world, the NZ Australian standards. They are great to have because they do establish the criteria for designing and providing good equipment. However, having more of that isn't going to create a safe work environment. Safety comes from the worker, has to have an appreciation for their own health and safety, and the only way that you can provide that is to provide them with education and proper training so they understand the consequences and what's going to happen. I was saying to Calvin prior to the start of the show that when we talk about H2S training, it's quite clear that if you're working in an environment of H2S, the consequences of working in that environment is immediate fatality.
Mm-hmm.
There's no two ways about it. You either use the SCBA and survive, or don't and die.
Mm-hmm.
It's that simple. Fall protection is a very similar thing. Not only is it the law for the employer to provide a safe work environment for their workers, but the worker needs to understand the consequences of falling. So I think that sums up the answer.
Yeah, and I really like the educational component. And whenever we talk about safety and driving safety culture, we say this is from the top down. It has to come that way. Otherwise, you're fighting an uphill battle. Yeah. And when you are the one saying, hey, we're going to step up our fall safety training, that communicates to the frontline workers that I care.
Yes.
So I think that is a very important thing to keep in mind, too, is when you get out there and you're serious about this, you can transmit that to the workers.
Yeah, and a lot of times the question has come up, and I know we're getting off topic here, but I want to bring this into, a lot of people say, well, how do I convince my CEO to spend the money on training and equipment and systems? You can show them the statistic on lost time injury, and then do some research as to what the cost of a lost time injury is to the company, and you can translate that into, rather than being safety training being a cost, it's an investment into worker safety. The worker morale goes up because now it shows the worker that the employer cares about them, cares about their safety, making sure that they...
And it's actions more than words, right?
Yes, yeah, that's a good way to put actions more than words. So, but that's a way to sell it to the CEO, because as Calvin said, if the CEO isn't on board and driving the safety from the top down, safety doesn't happen.
Yeah, absolutely. Actually, we have a webinar coming up in August on hazard assessment where we'll be covering a bunch of these talks as well. It'll be another safety talks. But on to the next question. How does a safety professional address the 6-foot rule when in most cases the worker will hit the ground anyway? Is the system worn only for looks? While I believe in ALARA, even with SRLs, the 6-foot rule is generally pointless.
Well, the 6-foot rule is established because of the statistic that I put up there for fatalities from a height of 2 to 4 meters. The human body, although God did a great job in designing us, He didn't design us for falls more than 6 feet. So that is why the U.S. OSHA has a 6-foot rule. So ways to protect yourself when you're at a 6-foot height is use other methods other than fall arrest. You could use warning line systems to keep the workers from getting close to the fall hazard of 6 feet. You can use guardrails. Guardrails is the most common method of protecting workers from fall hazards. You could use travel restraint systems so that the worker can get to the edge, but they cannot get past the edge and fall. You can use safety nets. There's a lot of other methods to use, but the 6-foot rule is established for the very reason that that's about what the human body can withstand as far as a fall goes, statistically.
Yeah, and I think this links back to the training question here, is when we communicate, hey, look at blunt head traumas at 7 feet.
Yep. I recall a story that I heard. A fella had a workplace fatality. He was the safety officer, and he was telling me the story that the worker had fallen from the back of a flat deck truck. He was tying the load down on the flat deck truck, and he tripped or slipped or whatever, but he fell off, and before he hit the ground, he fell head first into a large steel plate on the crane that was hoisting the load onto the truck. So he fell headfirst into the crane and then landed on the ground and was dead.
Yeah, and this question is a bit, I mean, it's a bit tough to answer, right? Because
Yeah.
we're all more or less in the same boat with this one, and it's just really look into it as much as possible. So we had a couple of questions about anchorage points. The first one would be, when can and can't I use a crane as an anchorage point?
Oh yeah, that's a good question. A crane can be used as an anchorage point as long as it is certified by a professional engineer, and you should have adequate procedures written for using the crane in that situation, because as long as the crane is being used as a fall protection anchorage, it cannot be used for anything else. It must be one or the other. It's either lifting a load or being used as an anchorage point for worker. And the procedures must include a lockout tagout procedure for the operation of the crane. You don't want to have someone get into the crane and operate that crane while it's being used as an anchorage point to secure a worker. So it can be used as long as it's certified by a professional engineer.
Yeah, and it kind of links into a question that's a bit more open-ended here, but what is the best way to assess an anchorage point? So
assessing anchorage points can be done in several ways. One is to have an engineer look at it and do an engineering analysis. Or another method is to do a pull test. You connect a pulling mechanism like a come-along and a load cell to measure the load, and then you apply a load of a test load of 2,500 pounds. And the 2,500 pounds is basically half of the ultimate strength of an anchorage point, which is 5,000 pounds in most jurisdictions. So that's a way to assess an anchorage.
Yeah, let's get to another one of the questions that we just had come in. So with mature workforce equaling high percentage of falls, more fall protection values geared to that workforce. So I guess, how do we address the high percentage of falls in that kind of 45 to 50-year-old range?
The older workforce?
Yeah.
Education. Train them. Don't let them bully you into thinking that they know what they're doing and they're going to be safe, and that won't happen to them, because statistically it will. And if they want to become a statistic, then they can go and work somewhere else, perhaps. You have to be stern. Safety has consequences, and rules of following safety must have consequences. If people choose not to follow the rules and not work safely, then there must be consequences to their actions. And unfortunately, that's the way I think it needs to be. That's my own personal opinion.
It's very important to look at those mature workers too, because whenever someone new comes into the workforce, I mean, who are they learning from? What habits are they
good point. The workforce does represent they're setting the example. Absolutely.
Yeah.
And if the older worker is the foreman or the supervisor or the manager, they need to be the ones towing the line.
Yeah, and when they're setting the example, when you have that key safety individual in there at that age, I mean, that's huge for a company.
Yep. When I do inspection work, I always use my fall protection. That's what I do.
Yeah, so let's jump into another one of the pre-questions here. So what basic needs are required for fall safety?
Basic needs for fall safety. This is, at face value, this seems like a very innocent question, or naive, or I don't know how to say that, but it's a good question, because it really, it's for the person that doesn't know a lot about fall safety, perhaps, and wants to know, well, what do I need to do? What do I need to know? So the best thing you can do is establish a managed fall protection program for your workforce, and that again comes from buy-in from the very top.
Yeah.
Establishing a fall protection safety policy, establishing well-written procedures, having a documented inventory of your fall hazards, associating work procedures to those fall hazards, having proper equipment and good systems to be used by the workers. And one of the most important things is worker training. Have your workers trained by well-educated, knowledgeable trainers, qualified fall protection trainers. you don't want to hire somebody that sort of knows what they're doing, or you don't want to bring in the safety salesman from the safety company who's selling you the equipment. You want to bring in somebody who actually understands the physics of falling, the consequences of falling, how the various bits of equipment are going to function, how the various pieces of equipment from different manufacturers will function, how the various equipment from different locations will function. You know, in North America, we've got Canadian equipment and American equipment, and although they're very, very, very similar, and they're manufactured in the same factory, they do adhere to different standards. And because they adhere to different standards, they function slightly differently. And then there's European equipment, there's Australian equipment. These equipments behave similarly different. They function in the same way, but they do it in a little bit different way. So you need to understand a lot about how equipment works.
Yeah, so we've got about 3 minutes left here. I want to make sure everyone gets out of here on time to make their 1 o'clock meetings. They're not running too much. So we're going to grab one more question. If you still have a question online, feel free to throw it up in the chat box. We'll try and cover it. But if not, as I mentioned, Doug will be available for a 15-minute phone call after this if you've attended, which thank you so much for that. Swing falls are always a concern in construction, hardly ever talked about. Yes, it's simple. Ensure your tie point is high and directly behind you. How much of a degree should one not exceed from side to side of the anchor point? So when we're thinking about anchor point here, how far does the worker go?
That's a very good question, and I understand exactly what you're getting at here. So I think what you're talking about when you say the degree, you mean the angle from perpendicular. I think what you want to be looking at, and I'm not sure if Juan is online here with us. I hope he is. But there's a couple of standards in CSA for window washing anchors, and they're Z91 and Z271. And they address not only the anchorage points, but the swing stages and that type of equipment that you would have on the side of a building for window washing purposes. But they do provide information on the angle that you should adhere to from perpendicular from the anchor. And I'm going off the top of my head, I think it's about 25 degrees total angle, so 12.5 degrees to one side of perpendicular, and then there's a limit on the distance that you would move, so it'd be 12.5 degrees to a certain distance, and then you don't go past that line. So again, very good question, but those standards should be able to help you. I don't recall the ANSI standard number for those in the US that may want to look at the window washing standard, but there's a very similar standard in the US in the ANSI library. And I'm not sure what the standard numbers are in Europe or Australia for that purpose, but I do believe there are standards in Europe and in Australia and other parts of the world.
Awesome. Well, with that, we want to make sure you get back to work on time, so I'm going to pass it over to Jamie for the exit here. Thank you for everyone coming out today. It's great to have you on the first Safety Talks with Doug Myette. It was a blast.
Thank you.
We'd like to thank both Doug and Calvin and everyone for attending today's webinar. We appreciate all the great questions, both during and before the webinar. And if we didn't answer your question, don't forget you can email Doug, and all attendees will have a 15-minute follow-up with Doug as well. Again, we'll be sending out a link to the recording and the presentation slides. And thank you again to everybody. Take care and have a safe and wonderful day.